Okay, excellent. Thank you. So I thank the organizers for the opportunity to be able to speak. I'm very happy to be invited to this program. This week I am away. I am only virtually there. In the next week, I will actually be there. So if there are longer questions, maybe you can ask them to me next week. So what I'm going to talk about is something I've kind of mystically called postmodern turbulence. And I have some examples of art going from traditional to the postmodern art. I will draw some analogies with this to turbulence research, but it's better done while I talk about this. So the classical part of turbulence research is the Kolmogorov theory. I guess there are lots of students involved today, so I'm mostly going to address them. The usual idea of turbulence is that you are getting the fluid stirred in some large length scales, and the energy cascade downs the scale. So going down the length scale, the energy is not dissipated. This is what is called the inertial range. Once it reaches the small scale where the viscosity has an important role, the energy do get dissipated, and that's the dissipation range. Typically, the power spectrum of turbulence shows a scaling. It shows a k to the minus 5/3 scaling, as I have taken from Frisch's book. And then it goes over to a much sharper decay, which is the dissipation range. This is usual knowledge. I guess everyone knows about this here. I am just trying to prepare the ground for the things I am going to talk about. So the term that is responsible for all the turbulent behavior in the Navier-Stokes equation is the advective nonlinearity. The way you try to understand this behavior, the one that you see in the power spectrum scaling, is the idea of scale by scale energy budget. So over here is the script E of K, which is the energy contained in all the Fourier modes from 0 to capital K. And then you ask, how fast does this energy change? So the rate of change of that is controlled by three different terms. One is the contribution from the advective nonlinearity, the pi k. One is the fk, the script fk, which is the contribution from external forces. And the last one is the dissipative contribution coming from viscosity. This is a reasonably straightforward calculation to do, starting from the Navier-Stokes equation. And now if you demand that you are in a stationary state, then the first term is 0. If you next demand that you are in a range of scales where the forcing is limited to small wave numbers and your capital K is much larger than those wave numbers, then this F is a constant. And then the last term, the contribution from the dissipation, you ignore because you are not yet in the dissipative scales. The thing that I just told you is not strictly speaking accurate. The various limits of viscosity going to 0, long time limit, and the limit of capital K is tricky and has to be taken carefully. But at the moment, I am not going into the detail and trying to give you a very simple qualitative picture of the behavior. So if you look at this first equation, it is the nonlinear flux that has to be balanced with a constant term. And if you look at the nonlinear flux, which in its detail is written down here, you will realize that the inside, you have basically three velocities. The square of one quantity multiplied by another. Written in real space, the quantity look like S3 by L, where S3 is the third order structure function, which is the following quantity. You look at velocity difference across a length scale L, take it to the power 3 and average. And the complete equivalent of this relation, that pi k is constant, will turn out to be this relationship S3 of L by L is minus 4/5 epsilon, where epsilon is the rate of energy dissipation. You might ask, how does that appear here? That appears because the rate of energy injection, which is the AF, must be equal to the rate of energy dissipation, which is the epsilon, in the stationary state. If you look at this expression, which is called the Kolmogorov 4/5 law, you realize that the third order structure function is proportional to L. Now, if you assume that the system has shows simple scaling, then that means that the simple velocity differences scale as L to the power 1/3, and the energy in the Fourier space goes as k to the minus 5/3. So this is the Kolmogorov picture, the classical turbulence, the traditional picture. But this picture is limited. There is more to the problem, and that brings us to modern turbulence. And the problem of modern turbulence is intermittency. So instead of looking at the energy, which is related to the second order structure function, you look at structure functions of pth order. Each one of them has a scaling exponent, and you plot those scaling exponent as a function of p, which is the zeta p versus p plot. In this one, the Kolmogorov, the K41 is p by 3, just as I had explained. There are various other models that give different behavior, but most importantly, the actual experimental exponents are not on a straight line. They are on a curved line, and this is showing that the system is not simple scaling. There is much more to it. Now, one can say that the system is strongly non-Gaussian, but just be a little bit careful here, because before we talked about the third order structure function, and we said that the third order structure functions in Kolmogorov theory is non-zero. That means Kolmogorov theory itself is non-Gaussian, because the third order moment in a Gaussian distribution is 0. So Kolmogorov theory itself is non-Gaussian, whereas here you have really extreme events. Within the Kolmogorov theory, the fourth order structure function you can conclude from the second order one. Here you cannot. This is the puzzle of turbulence, or what I often call the theoretical physicist turbulence problem. To find out what is zeta p versus p, starting from the Navier-Stokes equation. This is not done yet, and I am not going to talk about that, but this is the modern turbulence problem. And our understanding is that the reason the structure function behaves this way is because of fluctuations to the energy flux. So there is a connection between the fluctuations to the energy flux with the behavior of the structure functions. Of course, the energy flux is related to the energy dissipation rate. So you now see that the intermittency that is there in the inertial range is actually connected to the fluctuations of energy dissipation in very small scales in the dissipation range. This is the connection between inertial range and dissipation range intermittency, and I am going to mention it once. Importantly, this behavior, which is intermittent, can also be described by a multifractal model, and it's useful to look at this definition here. So the dissipation is said to be multifractal if there is a function capital F alpha, which maps the real scaling exponent alpha to the scaling dimension f less than equal to 3, such that for any alpha, the following relationship is true, which is log of the probability distribution of energy dissipation over a ball of scale L. So you take a ball of scale L, and you calculate the energy dissipation over that, and you look at its probability distribution. Then the probability distribution itself has a scaling behavior. Its log 1 should behave as 3 minus some function of alpha. This can be probed by looking at the various moments of the distribution, and from those moments, you can calculate the F alpha spectrum. Now, people calculate small f alpha or instead capital F alpha. This definition includes the capital F alpha, where the small f alpha is capital F alpha minus 2. This is the first demonstration of the multifractal behavior by Srinivasan and his group, which I have put here. So I have now talked about traditional turbulence and modern turbulence. And now I am going to talk about some things which are very strange in the sense that modern art is related to reality. So I am going to talk about turbulence in a way without the adjective term. So how can you have turbulence without the adjective term, given that the adjective term and the nonlinearity are the main reason for turbulence to exist? One possible way, or the only possible way, is to have some other nonlinear term in your equations. And I'm going to mention that in a moment. What I'm going to talk about in this part is described in the two following papers. So let's see if if this video works. So the person you see in this video is G.I. Taylor. Okay, so the main, well, if you can have GI Taylor speaking for you in any point, you should better use that. One of the main lessons from this is that if you drop the nonlinear term, you land up with the Stokes equation, and there everything is regular and nice, and there is no turbulence, there is no mixing, there is nothing, well, I would not say there is nothing interesting, but there is nothing of interest to a turbulence physicist. And these are the regime of microfluidics, or these are the regime over which, for example, sperms swim and bacteria move. This is the regime of very small scale behavior. Somehow this is okay. But in the last part of the video, you noticed that if you put a thread in the flow, that thread does not return back to its original position. That is because you have now introduced a new nonlinearity, which is the nonlinearity of the elastic filament. So instead of thinking of the Euler equation, you are now in the other problem in which Euler is famous, which is the problem of Euler buckling. So we are going to study this using a bit spring model, where I am going to model this thread as beads on a spring, and I put it in a shear which changes with time. So the shear is changing in the horizontal direction. So the velocity is 0 at the top and increasing at the bottom as the x component of velocity. And you notice that the thread moves and the thread comes back. And when it comes back, that's when it has developed buckling instability. So this is the most important part of the problem. So now that the elastic nonlinearity is in play, you can imagine that when the thread comes back, it may not come back to its original position. And if you repeat the experiment many, many times, each time you may get it in a different configuration. So what I am going to propose, what I am going to show in a little bit, few more slides, is that there is now a turbulent behavior of the thread itself as a function of its arc length. So how do you present a thread? The shape of the thread is completely specified if you specify curvature as a function of the arc length. And that's the quantity that is now going, that is soon going to behave as a chaotic function. So there is a lot of interest in this problem. People have been looking at threads in flows for a very long time, numerically and experimentally. But most of the time, they have been looking at flows which are steady in time. So here is an example of such an experiment. So there is a thread that is horizontal, and there is a horizontal shear. And when the thread, and there are these three different experiments where you change how stiff the thread is in some non-dimensional way. So in the first example, you see the thread tumbles, it rotates, and then comes back to its original position again. In the second one, a very similar thing happens, but it takes a different shape. In the third one, it takes shapes which are even more interesting. So all of these ones, these grayscale pictures are from experiment, and the blue lines are our reproduction of those experiments, changing the elastic constant of our thread. So this agreement is pretty good. So it is reasonable to believe that what I am going to show you next is also what you expect to see in an experiment. So what happens is, so here, what we have done is we start with a straight thread always, and then we look at the problem in cycles. So the shear changes, comes back, changes, comes back. So when the thread is very hard, it just rotates and comes back with no deformation at all. That's the case that I do not show. And now from top to bottom, I'm looking at softer and softer threads. And a very interesting phenomena appears. In the first case, you see the thread develops an instability, and then it remains in that shape. So at the end of every cycle, you will see this shape reappearing. What happens when you make the thread even softer is that you get into a two period. You start to get the shapes alternating. In the odd cycles, the shape looks like this. In the even cycle, the shape is a mirror image of that quantity. You make the thread softer again, you start getting quite complex shapes. And you make it even softer, you get into the regime where things are quite strange. For example, over here, you see it seems that the thread has almost reached a fixed state. It's a non-trivial shape, but it's a fixed shape nevertheless, although not exactly. If you look at 55 and 75, you will see very small difference between them. But in between, the process doesn't repeat. So why do I care whether the process repeats or not? So if you remember the G.I. Taylor video, what was being said is that if this thread follows or if the system follows a regular behavior so that every motion is being repeated, then the motion of every particle in the fluid is also being repeated. There is no mixing in the problem. The lack of mixing in a microfluidic device is the real challenge that one needs to solve, because you know that the microfluidic device has revolutionized biology and chemistry. But one of the major bottlenecks is that if you want two reactants to react, then you want them to mix. And in a microfluidics, mixing is extremely slow. So that's one of our motivation in looking at this. And for that, you need to have a motion of the particles that doesn't repeat themselves. So that clearly starts happening here. And over here, I will show you a phase diagram. So in the vertical axis, I'm plotting the time scale. So there are certainly two time scales in the problem. If you look at the shear and non-dimensionalize it, you get a time scale. And if you look at the frequency over which the thread goes and comes back, you get another time scale. The ratio of these two time scale is one dimensionless quantity sigma. And the other one, the mu bar, is the non-dimensional deformability of the thread. So we model the thread such that it just has a bending modulus and nothing more. And there is a length. So the non-dimensional quantity at the end is 8 pi. 8 pi is just conventional, multiplied by viscosity of the fluid, the shear rate, the length scale to the power 4 divided by the bending modulus. And you see quite a complicated behavior. You see that there is a region over which the flow seems never to repeat itself. This is most interesting to us. This is the part we call complex. There is a part over which the flow is complex, but for a long time, but at the end, the complexity goes away. The flow seems to settle down to a reasonably regular behavior. There is a part over which the thread buckles. There is a part over which the thread always remains straight. This is the regime over which the thread is very hard, or the regime over which the mu bar is quite small. And there is a part where you have two period, and there are parts where you get buckling solutions. So this is one of the interesting things that I am going to talk about, or I am talking about. And the way to understand it, well, we don't have a complete theory of this, but one of the ways to understand it is to proceed in the following way. Before I go into details, I will describe the equations that we have been solving for a little bit longer. So if you look at the thread and remember we are modeling the thread by beads on a string. So Ri is the location of every bead on the string. And I'm going to write down an equation for the evolution of Ri. So one part is just coming from the advection due to the shear, and that is the U naught. And there is the other part that is the interacting one. So what are the different forces that are acting on every element in the thread? One is the elastic force, and the elastic force comes from an elastic Hamiltonian, which is H, and a derivative of the Hamiltonian with respect to R gives me the force. So usually you would think that the equation will be second order in time because this is just Newton's equation. So, but we have taken the limit where you can ignore the mass, which is the right limit in these equations. So all you have left here is the M, which is a tensor, which is a not necessarily diagonal viscosity tensor. So you move every bead, you move any bead, every other bead is going to be affected because of the viscous interaction mediated by the fluid. We have integrated over the fluid degrees of freedom and written down the effective viscosity here as a matrix. And this is quite standard. This is done in many, many books, including, you can find essentials of this in bachelor also. And this is the evolution equation. So, but you see, the problem is a little bit tricky. If you want to think of the problem as a dynamical system, you now have a dynamical system that contains a term that explicitly depends on time, which is the external force, which has an explicit dependence on time. So such a dynamical system are not the easiest ones to solve. So the standard trick is to convert it to another dynamical system, which is time independent. And here we do that by think of the problem stroboscopically. So I look at the problem at the end of every cycle. So I integrate over this equation over one cycle. You can imagine that at this instant, before the shear is turned on, the thread is described by curvature as a function of arc length. And it goes over one cycle, and then there is a new curvature as a function of arc length. So I can say curvature as a function of arc length S at time capital T is a function of the curvature at arc length S at time 0. So this is the curvature map. And it's a map that I can't explicitly write down, but I can calculate it by integrating the differential equations. And the idea now is, what are the fixed point and periodic orbits of this map? Those are going to describe in detail the chaos that I'm going to observe. So the standard way to investigate fixed points and periodic orbits is to do the Newton's method, as you may know. And I guess everyone here knows what Newton's method is. But importantly, you are now living in a very large dimensional systems, and you can find out both the stability, both the fixed points and their stability with this. So once we do that, and I show you the results here. So I have two lines. The top line is, so I have taken a fixed value of sigma and going along different values of mu bar. So first I again show you the things that we observe from the dynamical equations. Top here, there is a straight line. Then there is a buckle shape. So these shapes are not exact shapes. They are curvature as a function of arc length. And here you see the curvature is 0, which is the straight line. Somewhere over here in the blue point, you get the two solutions, one which is a mirrored image of the other. And then you go over, you get other different two solutions. And this is what the dynamical system approach gives us. Initially, the only solution is a straight one. Then again, by going through the fixed points of the map, I start getting 3 of them. I think there are 4 of them here, and there are 2 of them, and there are many of them here, and then many of them over there. So I hope this convinces you that here is a problem where you see turbulence, but here turbulence as a function of arc length. And the way to see this is to use this method called Newton-Arnoldi, but I'm not going into that. We can talk about it next week if you are really keen on that. But I should tell you a few words about the method, the way it has made a lot of impression in turbulence research, in the way that on one hand, it has always been that the turbulence research is dominated. The people who work on turbulence are divided roughly in 2 groups. One of the groups that I mostly belong to, and I think these are the people you are going to see in this meeting, are the people who believe in statistics and don't worry about anything else. They basically say, look, if you look at a turbulent flow, you see many structures which comes and goes, but I don't care about the structures. I only care about the statistics. And there are other group of people who looks at a channel flow, and then they say, oh, there is a hairpin vortex here. And there is some other vortex which looks like something else there. And they seem to claim, or they claim, that the statistics is not important, is the structures that you see, the structures that are there for longer time but eventually disappear, they are the ones that are important. So these two camps, the statistic camp and the structure camp, has always been at a friendly war with each other over the history of turbulence research. And this is the idea that bridges them. So the idea that bridges them is to say that, look, every structure that you see contributes to the statistics with a certain weight. So how do you find that out? So how do you find the structures in a mathematically meaningful way, starting from the equations? The idea is that the structures would appear as fixed points with different varied degree of stability in the map. And once you calculate the stability of each of the exponents, each of the structures, sum them in a certain way, you will actually get the total Lyapunov exponent of the problem. But that's too long to go into at the moment. So over here, I also show you that if you put now some passive tracers in this flow with the thread, what happens to them? The passive tracers get mixed. So at t equal to 0, the passive tracers are on a circle, and they're colored by their position on the circle. At later time, they're getting mixed, and you can see that the colors are getting mixed, and even later time, the things are all over the place. To look at this in a more quantitative way, we look at the displacement of a passive tracer and calculates how far it goes as a function of time. But the time here is measured in the unit of cycles. So over here, you see how it behaves. If it is mixing, you would expect diffusion, and you would expect it to go linearly with p. From our data, this looks closer to p square. And how does that happen? You may think that this is actually Levy walk, but it is not. What we show is that there is no Levy-like behavior here. This curve we expect to go over to p at late times. To summarize, curvature as a function of arc length is a random function in space-time. This is turbulence. There are ways to do analytical attack. For example, if you use local viscosity, you still get chaotic solutions. And in an intrinsic coordinate, the dynamics can be mapped into a nonlinear Schrodinger equation, except for the external flow. So the problem always keeps one-dimensional, and we are working on analytical attacks on this. So that's the summary of part 1. Are there any urgent questions? If not, let me go over to the next part. So the next part is kind of related to this, but instead of thinking about a single thread, you think of many, many threads, but they are very, very small. So we are thinking of turbulence with polymers in it. This is a topic that is of a long-term interest, starting from the time when people found out something called polymeric drag reduction. So if you take a fluid and add a small amount of polymers in it, few parts per million, then the drag of the flow significantly reduces. This has been used in Alaskan pipelines and oil pipelines, and there are unbelievable pictures which have demonstrations of this, where adding a little bit of polymer to the flow can allow a jet from a hose pipe from a fireman hose to reach much longer than it normally would. But that's not the problem I'm going to talk about. I'm going to talk about polymeric turbulence, which is homogeneous and isotropic. And a related problem is what is called elastic turbulence. So elastic turbulence was invented, demonstrated around 2000 by Victor Steinberg and his group, where he showed that if you have polymers in the flow and your Reynolds number is extremely small, you can still get chaotic behavior or turbulent behavior. So you see, all these two together presents a very interesting case where you have a turbulence that is not the usual turbulence, but a very different turbulence. So the equations that describes the polymeric turbulence are written down here. Just stay with me for a little while. Parts of it you can see here. So the first is the Navier-Stokes equation. You can see the time-dependent term, the advective nonlinearity, the pressure gradient, and these two together is the viscous dissipation. And the final term is a reaction from the polymer. And the polymer is represented by a matrix, which I denote as C alpha beta. So a polymer, you can think, is a long molecule. So one way to represent it is by a vector, which is the end-to-end vector. And then you take a direct product of the vector with itself, you get a matrix. You average it over the thermal fluctuations, you get the C alpha beta. So now, in addition to the field, which is the velocity vector field, you also have a matrix field, which is C alpha beta, a symmetric one. And the matrix field itself obeys this equation, with time derivative depends on advection. And then there is a stretching term, which comes out of this too. But importantly, when you stretch this polymer, the polymer relaxes back. Okay. So there are two kinds of polymeric models that are considered. One is what is called an Oldroyd B model, where the polymer is modeled as a Hookean spring. And the other is called a Fene P model, where the polymer is modeled as a nonlinear spring, so that the polymer do not extend to infinite length. Okay. So that's the background. And I'm going to show you what we are going to get. Again, we are going to look at the spectrum of velocity fluctuations. And you see now that I am plotting the spectrum as a function of k for different Deborah number. So the Deborah number is a non-dimensional number, which is a ratio of the time scale, which is the typical time scale of relaxation of the polymer, over the large eddy turnover time, the largest time scales of the flow in the problem. In the first case, you see that there is a scaling behavior, but the scaling behavior for a small Deborah number is practically Kolmogorov. This dashed line is the Kolmogorov line. Now you increase the Deborah number and you are at a Deborah number of almost 1. You notice you can still get a scaling behavior, but this is not Kolmogorov anymore. I will show you in a moment, but trust me for a few minutes. What it looks like, what it almost looks like, is that there is a scaling behavior over here at relatively small Fourier modes, which is Kolmogorov-like, which is the dashed line. At much larger Fourier mode, it goes over to something else. This is at Deborah number of 1. And once you go over to very large Deborah number, you see the system has gone back to Kolmogorov behavior. There is still a small range of scaling, which is not Kolmogorov-like, but largely it is Kolmogorov behavior. So people have called this and similar problems elasto-inertial turbulence, where both the elastic forces and the inertial forces are important. But this is the same field that has always been called polymeric turbulence. I am showing you numerical experiment. But before our paper, actually our paper was largely inspired by a set of one experimental paper from the group of Eberhard Bodenschatz, where they also saw exactly the same behavior of the energy spectrum or the power spectrum of velocity fluctuation as a function of Deborah number. So here I am plotting the compensated spectra. This is one of the ways to see your scaling exponents. So on the left, what I am doing is I am taking the same energy spectra and multiplying the energy by k to the power 5/3. If I do that, I will get a straight line in the Kolmogorov range. So over you see, for small Deborah number, there is a reasonably large straight line, almost a decade. So you have Kolmogorov behavior up to a decade. And then as Deborah number increases, the Kolmogorov behavior decreases. In the red one, it is quite small, and then increases again. There is non-monotonic behavior. But this is what happens at small k. What happens at large k? In the large k, there is a different scaling exponent, which is 2.3. And you notice that as you increase the Deborah number, over here at small Deborah number, that range is practically non-existent. Excuse me. And then it increases. And in the red one, it's a pretty long one. It's almost a decade. And then it decreases again. So there is this remarkable behavior now that you have elastic behavior, not elastic turbulence, but elastic behavior at scales which are larger than a certain scale. And at scales which are smaller than that scale, you get the inertial or the Kolmogorov behavior. So how do you understand this? Of course, the first step to understand this is to look at the flux. Just as I told you in the beginning, we again calculate the flux, and this is the same E of k and the pi of k and everything that is described in the beginning of the talk, except there is a new term P of k that is coming from the polymeric contribution. The polymeric contribution is a little tricky. You see, one of the first thing a polymer does to a flow is to increase the viscosity of the flow. Typically, whatever you add to the flow increases its viscosity. Goes back to the calculation by Einstein, where he showed that if you add small amount of pollen grains to a flow, then the effective viscosity of the flow increases. You can imagine that if the polymers are not going through strong stresses, then they're curled up like ball, and then their addition to the flow is like adding small particles to the flow, and their effect is just to increase the viscosity of the flow. So to do that, we divide the polymeric contribution into two parts. One part that looks like a viscous contribution, and we define it as taking the fluid viscous contribution and multiplying it with an effect, with a term that looks like polymeric viscosity. And the rest of it is what we call pi p. This is a completely synthetic decomposition. It's just there for us to help understand what is happening. What you see is when the Deborah number is very small, the term P is very small. So the usual picture of the turbulence works, you get Kolmogorov behavior and Bob is your uncle. As the Deborah number increases, you get this very interesting situation where you see a separation. This is the part where the inertial term has almost gone to zero, and it is dominated by not P, but the pi P, which is the non-dissipative part of the polymeric contribution. And this is a range over which it is the dominating term. And then at high over Fourier number, it decreases again. So this is the range over which you will see the new scaling. This doesn't give you a theory of the scaling. This just tells you that the whole picture is consistent. What you see is meaningful. The theory, of course, is not there yet. But very interestingly, and this is the most intriguing part of the problem, what happens when you look at the intermittency in the problem? So there is intermittency in both the ranges. See, you can calculate the structure functions, and the structure functions in the Kolmogorov part departs from the Kolmogorov behavior by a small amount. You can calculate what this small amount is, and you obtain what you would obtain if you didn't have any polymers in it. Okay, not a great surprise.
Hello?
Hello?
Could you finish in about 4 minutes?
I will. Thank you. So you look at the part which is slightly more than which is slightly different from the Kolmogorov part, and there's no surprise there. The most interesting part is if you look at the part where is the elastic forces dominate, you also have intermittency exponent. And you realize that the intermittency exponent, you find out that the intermittency exponents are exactly the same. So you see, the most surprising thing has happened. Your second order function, the scaling of it has gone over to a different value. But the intermittency corrections about that value remains exactly the same as you have seen it in the flow. So how do you understand that? One of the ways to understand that, what we calculated was instead of looking at the inertial range intermittency, we looked at the dissipation range intermittency. So we looked at the fluctuations of the energy dissipation, and from that we calculate the F alpha spectrum, and over which I have plotted the sky blue lines, which is the Srinivasan's results, and they fall exactly on top of each other well, with reasonable approximation. So to cut a long story short, what happens here is the following. You have two fluxes, one from the polymer and one from the fluid. But at the end, you again have two dissipations. One is the fluid mode and one is the polymeric mode. the fluctuations in the fluid mode are much larger than in the polymeric mode. I haven't shown you that plot. And it is these fluctuations that control the fluctuations of the flux. So the mean value of the flux changes, but the fluctuation is something remains the same. And that's why you get exactly the same intermittency exponent. We don't have a theory of the intermittency, but we have been able to understand why it is the same intermittency as what you see in the flow. So that's the summary of part 2. So the first part of the work has been done with my student Vipin Agarwal, who just graduated in December. The second part is a collaboration between myself and Marco Rosti, who is at IISc in Japan, Prasad Pendekar, who is in TIFR Hyderabad, and now Rahul has also joined the team, who is possibly physically somewhere there among you. Thank you very much for your time.